Okay, ladies, so today we're talking about p-values and further into how we test for a claim. Okay, ladies, so we're going to talk about p-values. And this is super important for the rest of the semester. So p-values are a probability computed assuming that the null hypothesis is true. So this is the probability that the statistic would take a value as extreme or more extreme than the one we actually observed. And we actually calculated a p-value even though I'm not sure that you knew that we did. So with the baller example that we were talking about yesterday, she said that she claimed that she shot free throws at an 80% success rate. So 80% of the time she was there. When we actually calculated p-hat, we found that p-hat was 0.64. So then we looked at a distribution, and we were looking at if the true value was, the true mean was 0.8, and she was like, what's the time that it's going to be 0.64? And there were only 3 times out of 400, if you'll remember from this lovely little picture, that 0.64 actually occurred, or less than 0.64. So that ended up happening 0.75% of the time. And we said that's really small. So what we were actually doing is calculating a p-value, the probability. Okay, so smaller p-values are stronger evidence against the null hypothesis, right? So let's say our p-values are really, really, really small. If that is the case, then the observed results are unlikely to have occurred by chance. So it's unlikely that if she truly was 0.8, 80% of the time she hits the free throws, that this is unlikely to have occurred by chance. Like, it's not likely that we would have gotten this percentage by chance. Okay, if you have a really large p-value, it fails to give convincing evidence against the null hypothesis. So the results are likely to have occurred by chance when the null is true. So essentially what's happening here is our p-value is a conditional probability, and you're not going to like this, but here it goes anyway. So we have the probability of p-hat is less than or equal to some value, some number, right? Given that we have this for a null hypothesis, right? So what's the probability that we will get p-hat of this value or less given the null hypothesis? So it really is a conditional probability, which is glorious. So then here we go. Conclusion. When we say, okay, well, look, she got 0.64. That means there's no way that this could ever be true. We don't say, our conclusion will not be that the null is ever true, even if this turned out to be true. What we say is, if we found out that her probability was actually close to 0.8, we would say instead, we fail to find strong evidence against the null hypothesis. Okay, so that's kind of a weird way to word it, and you really, really have to understand this concept, that even if the data says that the null could be accurate and true, all we're saying is we don't have evidence against the null. So we can't say the null is true, we don't have evidence against it. Okay, so let's look at p-values as an example so you can try to figure out what in the world I'm talking about. So let's say Simone reads a newspaper report claiming that 12% of all adults in the United States are left-handed. She wonders if 12% of the students at her large public high school are left-handed. Simone chooses an SRS of 100 students and records whether each student is right or left-handed. Okay, so in that particular scenario, we're going to have a null hypothesis, an alternate hypothesis, and we need to define our what p is, what the proportion is. So you can pause if you like, think that through in your head. So I'm going to go ahead and do this. So I would say that my null hypothesis is the probability, so that's essentially my claim. So I'm saying, okay, p equals 0.12. And then for my alternate hypothesis, it's not telling me whether or not it's more than 12% or less than 12%. So I have to assume that it is both above and below, which means in my alternate hypothesis, what I think might actually be true is that it is not 0.12. Okay, and then P is going to represent my true proportion of lefties, left-handed people, in Simone's school. All right, so continuing on. In Simone's SRS, 16 of the students were left-handed. I immediately just pause for a second and say, oh, okay, 16 out of 100, so that's a p-hat of 0.16. I don't know that I need that, but there you go. A significance test yields a p-value of 0.2184. Interpret this result in context. Okay, so basically I kind of have to explain what's going on. So the way to phrase this is, if the proportion of lefties at Simone's school is really 0.12, there's a 21.84% chance of finding a sample of 100 people with a value of p-hat that is as far from 0.12 as the sample value in either direction. All right, and you're probably wondering what in the world I just said, but essentially what I'm saying is, okay, here's a picture. Normal distribution. This is our mean. This is the worst. Okay, mean p-hat, and we found that to be 0.12. This is what we think the true mean is. So if the true mean is this, and we're trying to go above and below this, and we actually got a percentage or a p-hat value of 0.16. So 0.16, I would look at the difference between 0.16 and 0.12 and say, okay, here's another difference. The difference above and below this, I have the above, the below would be let's see, maths, 0.08. And I want to know, what are the chances that we're here or we're here? When I add those two together, that's actually my p-value. Now don't freak out, I know I went too fast. We're going to be spending some quality time talking about how one calculates p-values, but for right now I just want you to get the gist of what a p-value is and what it means. Okay, so basically it means there's a 21.84% chance that you could actually find this p-value knowing that assuming that the null was in fact true. So 21% chance, that's fairly high. So does the data provide convincing evidence against the null hypothesis and explain? I would say no. 21% is something high, something that happens over 20% of the time just by chance when the null is true is not really strong evidence against the null. So I have to have strong evidence against the null, or convincing evidence against the null. You're going to see this a lot. So 20%, that's just too big. Okay, so now that we've looked at our data, we find a magical p-value. Again, we're going to learn how to calculate this magical p-value a little bit later. But we have this p-value. How do we draw a conclusion from it? Well, since the p-value is really a conditional probability, and it says that, you know, this is the percent of time that this should happen when the null hypothesis is true, it gives us a way to draw conclusions. So essentially, the last step in performing a significance test is looking at our p-value and drawing a conclusion. So you're going to make one of two decisions, and there's only two, based on the strength of evidence against the null, aka the p-value, right? And this is very much like when we were doing conclusions in science. You write a hypothesis. You either accept your hypothesis or reject it. There were two choices. And we're not going to accept our hypothesis in this case. What we're going to do is say that we either reject the null, that's something you're familiar with, or this is fun, we fail to reject the null. So we never say, oh, this is all good, this happens. We say we reject it or we fail to reject it. This is so important to get this idea that we either reject it or we fail to reject it. This wording is very, very crucial. The easiest way that I can describe this whole idea of we have two choices, we reject the null or we fail to reject the null, is with this. A criminal trial example. Okay, so basically in our court of law, we are innocent until proven guilty. So it's similar to guilty versus not guilty verdicts. We never say that someone is innocent, right? You never ever prove that, and we never prove the null hypothesis. We simply say that we are going to reject the null or we fail to reject the null. So it's similar to guilty versus not guilty. Yeah, not guilty implies innocence, but not exactly. It just means that we didn't have enough evidence to find them guilty. And that's the same that's true with the null hypothesis. If we have enough evidence, we can reject the null. If we don't, then we fail to reject it. Okay, so how do we draw a conclusion? Well, essentially, we calculate a p-value. Again, later, we'll learn about this, based on the theory that the null hypothesis is true. So if your p-value is small enough, that provides convincing evidence against the null. What does this mean? This means that what you got, the sample that you got, the results that you got, are unlikely to have occurred by chance. It's a very important phrase here. So what that means is that our sample is so unlikely to have happened by chance if we assume that the null is true. So we have to assume that the null is not true. So we reject the null in favor of the alternate hypothesis. If p-value is too big, this does not provide convincing evidence against the null. So the means sample results could have been due to chance is essentially what that means. So it's possible that if we have a p-value high enough, then it could have happened by chance, so we fail to reject the null. Okay, ladies, so the question is, what's that line for rejecting the null or failing to reject the null? Is it 15%, 20%, whatever? And the way we come up with that level is from levels of significance, which we write as alpha. And levels of significance, the alpha really comes from your confidence level. So let's say your confidence level was 95%. That means your alpha is 5. If your confidence level is 90, your alpha is 10. So it's really essentially what it's saying is, if you choose an alpha of 0.05, so that's 5%, so that would be a confidence level of 95%, just to say it in a bunch of different ways. We require that the data give evidence against the null so strong that it would happen less than 5% of the time if the null was true. Okay, so how do we figure that out? We compare our p-value with alpha. So we look at the p-value, and again, we're going to talk about how to get that, and we look at our alpha. So if the p-value is smaller, you reject the null. If the p-value is bigger, you fail to reject the null. And it's just that simple, except for this is like life, key, so important, memorize now. The way that I memorize it is if the p is small, the null must fall. But that's kind of silly, and I'm sure you can come up with a better way. But essentially, like, if the p is small, reject the null. Or another way, if you like this one better, if the p is low, the null has to go. It's not as good, but whatever. You get the gist of this. Memorize, memorize, memorize. If you don't get this right, this is going to make the whole rest of the semester really, really, really bad. So, or really, really, really good. So make sure that you know this. Okay, enough of that. So if the p-value is less than alpha, we say that results are statistically significant. And I'm very, very, very careful to use this word. So what does statistically significant mean? That it is not likely to happen by chance. That's essentially what it means. But we've proven that with statistics by saying that our p-value is less than alpha. So a lot of people use the term statistically significant or significantly different data. And when you say it's significantly different and statistically significant, then we're talking about a very, very specific thing. P-value is less than your alpha. So keep that in mind. You cannot use the word significant unless that's true. So again, it means it's unlikely to have just happened by chance. Okay, so big takeaways. If the p-value is less than alpha, we reject the null in favor of the alternate, and we would put this in context, right? So we would conclude the alternate hypothesis in context, and we would say the results are statistically significant. If the p-value is greater than alpha, we fail to reject the null, and we cannot conclude that the alternate hypothesis is true. And again, we do this all in context. So it's always good that whenever you're doing an actual study, if it's good, they should report the p-value so that you can compare the p-value to the alpha to see if in fact their claim is accurate. This is not always done though. Okay, so here's an example. For her second semester project in AP Stats, Keisha decided to investigate whether students at H&A prefer brand name chips to generic potato chips. She randomly selected 50 students to try both types of chips in random order. Overall, 34 of the 50 students preferred the brand name chips. Keisha performed a significant test using the hypotheses. So her null was the p equals 0.5, meaning that if it's 0.5, it's a 50-50 shot, meaning that they don't actually have a preference to potato chips. So that's the null hypothesis. And the alternate is p is greater than 0.5. So I'm not sure what her proportion is, so this is why it's very important to define it, where p equals the true proportion of students who prefer brand name or name brand chips. So again, the alternate hypothesis is that they will like brand name chips better. And then we have a magical p-value that appeared out of nowhere. We have no idea where it came from. We'll deal with it later. Okay, so what conclusion can we make at each of the following significance levels? So my first significance level is alpha equals 0.01. So I'm going to state my p, which is 0.0055, and I'm going to look at my alpha, 0.01. Okay, so it looks like, boom, p is less than our alpha. If the p is low, the null has to go. Reject the null. Now I can't just say reject the null. I would say since the p-value is less than alpha, and then I would put in parentheses these values here, we reject the null hypothesis. There is convincing evidence that the students prefer brand name chips. Okay, same game over here. Same p-value, but now we have a different significance level. So we're saying that here's our p, and our alpha is 0.001. In this particular case, p is higher than our alpha. And yeah, p is higher than our alpha. So because p is higher than our alpha, we can't reject the null. We fail to reject the null. And of course we have to put this in context, so we would say since the p-value is greater than the alpha, and we put this all in parentheses and state these numbers, we fail to reject the null. There's not convincing evidence that the students at H&A prefer brand name chips. Now, occasionally we are human and we make mistakes. And so we need to talk about these errors. These errors are kind of important. They're called type 1 and type 2 errors. So there are two possible. The first is the idea that we reject the null when the null was in fact true. So we found out the null was true, but we decided to reject it anyway based on the data. This would be the equivalent of giving a verdict of guilty when the defendant is innocent, and this is considered a type 1 error. Okay, the next type of error is that we fail to reject the null when the null is false. So this would be saying not guilty when the defendant is in fact guilty. And this is considered a type 2 error. And generally this is considered a worse mistake statistically. Okay, so visually, type 1 error, false positive. This doctor telling this man that he's pregnant. Type 2 error, false negative, a very pregnant woman, doctor telling them you're not pregnant. So I think that describes the type of type 1 errors, false positive, false negative. I really like this chart the most because I think it really kind of sums everything up. So here we have the actual truth about the population, and this is the decision we made based on our sample. So this would say if the null is true, and we decided to accept it, which is really fail, right? Fail to reject. Let's just fix that. Okay, then we've made the right choice. Good job, A+. if the true population, if the alternate hypothesis is true, and we decided to reject the null, again, woohoo, good choice, we made it, woo. Problems come into play when the null hypothesis is true, but we still decide to reject it. This is called a type 1 error, and it's essentially our alpha, right? This is our confidence level. How cool is that? So that's essentially what happens is the null was in fact true, but we rejected it based on the data. So we've hit that small error in our alpha. Okay, the type 2 error is a little bit different. So this would be the alternate hypothesis is true, but we failed to reject the null. So essentially we said, well, we don't have enough evidence to reject the null, but the alternate was in fact true. This is calculated with a value called beta, and this is calculated as 1 minus beta, and it's also referred to as the power of the test, which is a term that comes up. Anyway, so basically winning, winning, sad, sad.